There we go. A 68 kilogram student stands on a very light, rigid board that rests on a bathroom scale at each end as shown. What is the reading of the left scale? And then what is the reading of the right scale? Okay, so how much does the left scale read? How much does the right scale read? All right, so that's pretty cool. Kind of like the last one, but a little bit more complicated. Actually, not really more complicated, because in the last one there was really that hinge force. They didn't ask us about it, but it was still there. All right, so let me draw this one out, actually. So it's really important to have a nice picture with these, because you really have to see where the forces are acting to be able to calculate the torque. Okay? So I'm just going to do the problem like this. I'm going to say on the left, there's normal left, and then there's normal right. Those are the forces from the scale. And then I'm just going to put, so the student standing on the board, the weight of this student is pulling the student down, but there's a normal force on the board from the student that is really what's pushing down here. So I'm just going to call this the weight. It's not really the weight, it's the normal force from the student on the board, which is actually equal to his weight. Does that make sense? The picture? Scale, and then it's technically the normal force from the student, but it's equal to the weight, so I just wrote weight there. Okay, this is 1.5 meters, and then all the way to the edge is 2 meters. Okay, and then we're free to pick whatever pivot point we want to. So the first part is to figure out normal left. The next one is to figure out normal right. And I'm going to do this by balancing torques. Now I could try to do it with forces. So before we did this chapter, I could try to do this with forces. Normal left plus normal right is equal to the weight. That's perfectly right. Normal left, normal left, which is up, plus normal right is equal to the weight. That's good. The only problem is, I know the weight, I can calculate the weight, it's equal to m times g. The problem is I don't know normal left and I don't know normal right. So I have one equation right now with two unknowns. I can't solve that. I don't know normal left, I don't know normal right. One equation, two unknowns, I can't solve that. So I'm going to have to use torques to solve this. And as you heard, you can pick any pivot point you want. If I pick this as the pivot point, then I got normal left providing a torque about that pivot point, and normal right with a torque about that pivot point. But if I pick normal right as my pivot point, so I'm going to just pick that as the pivot point, then that force doesn't have a torque because it's right at the pivot point. It's trying to open a door with from the hinge. Okay, so let me write this equation, and this will make sense to you, I think. So about this pivot point, we're going to balance the torques. So the torque, because of the weight, making it go this way about this pivot point, has to be equal to the torque from normal left. Okay? So about this pivot point, this torque has to be equal to this torque, because it's not going anywhere. So this would be weight, and then distance to the pivot point, this is 0.5 meters, right? From here to here is 0.5 meters. That has to be equal to normal left, and then the distance to normal left is 2 meters. And then I can figure out normal left. So this would be weight times 0.5 meters over 2 meters. Okay, and the weight is m times g. So the student was 68 kilograms. And then to make it a weight, times g, 9.8. And then 0.5 divided by 2 gives us normal left. So I got 68 times 9.8. And then 0.5 over 2 is 0.25. 166.6. So that's what normal left has to be. Once you have normal left, you can go back to the force way of doing it if you want to figure out normal right. Let me write this on the picture here. 166.6. Okay, and then normal right has got to be equal to the weight minus normal left. So same thing, 32 kilograms, 9.8 minus normal left. I'm running out of room. This is what it is. I didn't have a spot to put it in there. Right, let's see what this one is. 32 times 9.8 minus 166.6, 147. So that's what this one's got to be. Okay, and then the weight, I'll just multiply this thing out. 32 times 9.8. This was 313.6. Okay. So the way I did this was to balance the torques about this point to get normal left, and then I used just balancing forces to get normal right. Let me verify that this is actually correct in one more way. Any questions about what we've done so far, though? It's good, okay. Let me pick this as the pivot point. So I'm going to pick this as the pivot point and confirm that the torques are actually balanced about that point. So just for fun, I want to do this. I'm going to balance the torques about this point. Now I said that you can pick any point you want to. Let's actually see if that works out. So if this were the pivot point, it's 1.5 meters to the weight. So the weight times 1.5 meters should be equal to, that's my notation there, is it equal to normal right, and then times this distance, 2 meters. Are those equal to each other? So let's see, 313.6 newtons times 1.5 meters. Is it equal to normal right, which is 147 newtons at 2 meters? Okay, so 313.6 times 1.5. Okay, so 313, 1.5, okay. 470.4. Huh, it's not going to work out. I wonder what I did wrong here. Well, good. It's a good check to see what I did wrong. 147 times 2. 294. So I've done something wrong because these have to be equal to each other. Anybody see what I've done wrong? Weight is 32. The weight is 68. I use 68 here. For some reason I put this student on a diet over here. Okay, so 68 is the mass. Here I use 32 as the mass. Why I did that I do not know. So this should be 68 times 9.8. 666.4. 666.4. Okay, and then this should be 68 kilograms times 9.8. So what I just did, and then minus normal left, which was 166.6. So this should actually be. Okay, let me do that one again. Minus normal left, 166. 499.8. Okay, so make a correction on that. I did the physics part right, but then I wrote 32 instead of 68. Now let's go back here and see if this is right. So normal left is 166. This is normal right is 499.8. Okay, and then we can see if this works out. So this again is 666.4. And then normal right is 499.8. Okay. So 666.4 times 1.5, 999.6. And is it equal to what we have over here? 499.8 times 2. Good. Same thing. Good. So they actually do balance each other. Whew, all that work and their mass was wrong. That's okay though. That's how it goes, right? Excellent. All right, any questions on this one? All right, so let's leave it for that for today. Group B will meet tomorrow. I'll make a video for Monday, which will be finishing up Chapter 8, which we don't have much to go in Chapter 8. And then we'll be going into simple harmonic motion, which I think you're going to like. Motion that repeats itself. We'll watch a video of the Galloping Gertie. Is that what it's called, Rick? The Tacoma Narrows Bridge. So if you want to look that up, you can look up Galloping Gertie and see what simple harmonic motion gone wrong is all about. Okay, any questions on anything? All right, very good. That's all for today. Then if you have any questions, stick around. We can talk about whatever you want.